Good morning, everyone. Hope you're excited as I am to learn about Transient Plasma Systems. I'm the CEO. So let's jump right into it. There's more than 22,000 deaths due to NOx and particulates in the United States alone every year. More than 9,000 of those are in my home state of California, and most of those are actually in our company's home city of Los Angeles. So if you look at the worst offender of NOx and particulates, it's on-road vehicles in the United States. There's more than 12 billion pounds of NOx, about 12 billion pounds, about 400 million pounds of particulate matter, and we spend about $400 billion on fuel every year. With TPS technology, we can potentially reduce NOx emissions by up to 90%, particulate matter by up to 70%, and save about $80 billion on fuel every year. And the biggest part of this is that we can potentially impact 18,000 lives in the United States alone every year by just applying our technology to on-road vehicles. And I say just because we actually have applications in marine diesels, in locomotives, and aircraft as well. So let's jump right into the technology. What we make are devices that deliver ultra-fast, nanosecond-long, high-voltage pulses. So these pulses are so fast, the energy is very small, but we're able to put in the power of 6 semi-trucks in one tiny little pulse. And we're using this to ignite a fuel-air mixture and fundamentally alter that combustion chemistry. So to take a look at how we alter it, we have to look at what exists today. Ignition has not changed in gasoline spark ignition engines in more than 100 years. So let's take a look at what that is. That's a spark ignition. I'm not sure how many of you are familiar with this. It's just like the spark in your stove. And basically what you do is you ramp up a high voltage, and eventually it causes a breakdown, and a spark jumps across that gap. Through that single channel, all of the current flows and heats up the air. This is a very inefficient way to transfer heat. It's like holding a match to the flame. About 1% of the energy in that spark actually goes into the fuel. What we do is we cut off that high voltage pulse before that spark can ever form. There's no breakdown, so we just have an ultra-fast electric field. And the result is this. We get a non-thermal, what we call a transient plasma, because it's transitionary. And in this case, all the energy goes into producing energetic electrons directly in the gas, rather than through heating. We call it non-thermal because you can stick your hand in it, it's cold. We'll actually show you a photo of that in the next slide. And in this case, 60% of the energy goes directly into the gas instead of 1. And we have the added benefit of this being distributed volumetrically. So you get distributed multi-point ignition. So with the added chemistry and the multi-point ignition, we can actually improve the efficiency in engines by about 20%. I'll show you the data a little bit later. And reduce emissions in that case by more than 50%. There's another application that's not just for spark ignition engines. I'm not going to talk too much about it now, but feel free to come to my booth and ask me about it, where we can actually apply this technology directly in the exhaust of diesel engines, for example, and treat the emissions that way through oxidation of the NOx and particulates. So there we're actually seeing a 90% reduction in NOx. We're seeing 70% reduction in particulates. And my colleagues were actually just on a ship this weekend. I couldn't participate because I was traveling here. But a program sponsored by shipping company TCC, they were able to measure SOx as well on actual heavy fuel oil on a ship out of Oakland Port. They're seeing about a 30% reduction in SOx. So this technology did not come out of nowhere. This came out of the University of Southern California. My PhD advisor, Martin Gunderson, had been working on the Pulse Power Group for about 30 years, making these ultra-fast pulses and applying them to all different things. He had the idea for applying these to ignition in 1994 when they were looking at applying the pulses to diesel engine emissions for NOx remediation and trying to understand the chemistry and physics of that process. Since then, the technology has substantially reduced in size. When I first joined the group in 2006, we were looking at a system that was about the size of a microwave. Just prior to that, it was about the size of a fridge. So even though I showed up and we were working with the Navy and the Air Force and some car companies doing demonstrations, even though it was working well, it was kind of like, okay, well, you're not going to put something this big in an airplane. You're not going to put it in a car. So what we've been able to do in the past years is to leverage advances in high voltage switching and significantly reduce the size of the technology. So we have the background IP from the university. We formed the company in our garage in 2009 just to address an immediate market of there being more demand for research on nanosecond pulse power. So we are entirely funded by the revenue of selling our research devices to about 50 laboratories around the world that are looking at using nanosecond pulses. So we have a great technology. We needed a great team to bring this to market when we realized this is actually small enough, efficient enough to go into commercialization. So we have the best pulse power team you could possibly have in the world. This is a small field. We go to conferences that are about 300 people. My PhD advisor, Martin Gunderson, is still heavily involved, works with us on a weekly basis. He's still a professor at USC. He's the world leader in pulse power, in particular nanosecond pulse power. Andy Kuthi, also on our technical advisory board, is the research scientist who taught my colleague Jason and I everything we knew about the technology to the point when we could then go run out and develop our own knowledge. Jason Sanders is my friend and colleague from the first days of getting this going in 2006 at USC. We've been working together since then, and he is truly brilliant in this technology. He is unmatched in his talent in nanosecond pulse power. So we run the company right now. There's 6 people in the company, and we have an extended experience on the board. We knew we needed the business talent. We very much believe in knowing what we're good at and adding to that as much as we can through other people's experience. Our board chairman is Mike Mann. He's the CEO of both public and private companies in the past. He was a senior executive in aerospace. Mario Leone is our automotive advisor. He's a former senior executive from Fiat Chrysler. And we have Hoshi Printer, the former VP of finance from Xerox. So getting this technology to market, it's a huge market. You have to have a strategy to actually get this out and make an impact. So what we did is we looked for a market that had a time-critical need where there was no cost-effective alternative, and that led us to natural gas. So if you take a look at the rising cost of diesel fuel, we've heard some of this today, truck owners are actually looking for an alternative. They spend about $45,000 a year on fuel on average, and they're looking at natural gas and saying, okay, it's cheaper, it's more stable, domestic source. And they're saying, okay, well, if I can convert to natural gas, I can save about $20,000 on fuel costs. So the question is, why aren't they doing it? Because they're not. You can read a Wall Street Journal article relatively recently about this. It's not happening as quick as we'd like. And one of the major challenges is actually technical. The ignition temperature of natural gas is about 3 times that of diesel fuel. It makes it very difficult to ignite with any kind of stability. So now you might be thinking, but I've seen natural gas vehicles on the road. There's a garbage truck, there's a bus, there's a Honda Civic. So what are they doing? Well, they have to make engineering compromises in order to put those vehicles on the road. So what they're doing, if they need the torque and the range of diesel, is they do dual fuel. They spray a little bit of diesel fuel in the cylinder, it starts to burn, raises the temperature, and then when they spray in the natural gas, it'll ignite. The problem with this solution is it adds overhead, both physically and in cost, and it requires exhaust aftertreatment that requires frequent fluid replacement. So if you don't care about the range so much, so for example, a municipal vehicle, a bus or a Honda Civic, you can sacrifice range by reducing the compression ratio and then increasing the energy for ignition. So in this case, you can dump about 10 times the energy of a traditional spark into that spark plug, and you can run the engine. This is what the little Honda Civics on the street do. Some of the buses do this. The problem with this is now you start melting spark plugs, because remember I said that that spark is 1% efficient. A lot of that energy is going right into the spark plug. So if you're driving around a Honda Civic, maybe it's fine, it's local. But if you're running a natural gas engine for power generation, where it's making money while it's running, anytime that engine goes down, you're losing money. And in the average case, they lose about $10,000 an hour to bring the engine down and to put the new spark plugs in. And currently, the OEMs are doing this every 16 weeks. So they're looking very actively for alternatives. So now the question is, why hasn't this happened sooner? What's going on with advanced ignition? Why is it unchanged? Well, if you look at this chart, you can see a nice line, which shows that as you increase the energy delivered, you increase the effectiveness. You get better ignition. And that makes sense, because we're putting more energy into thermal ignition. And in this case, they're all following the same line. All 3 of the ones on the left, other than laser ignition, are technologies that are currently available today. The 3 on the right are ones that are being looked at for the future of our gasoline engines. Transient Plasma Systems technology is the only one that gets outside of this curve. You can see where we're sitting on this plot. We're less energy and more effective, and we know this because we've tested against these technologies in national labs. So the best way to do this is to show you rather than tell you about it. So take a look at this video. On the right-hand side, you can see ignition of natural gas with our technology. On the left hand, you see it compared directly, same conditions, same time frame with high-energy spark. This data was taken at UC Berkeley and Professor Robert Dibble's lab. So thanks to Daniel, Ben, and Tim for taking this data. So this is a great way to show, actually, in an operating environment, what our technology can do. So the natural gas OEMs are really excited about this because it potentially solves their problem. Because it's low energy ignition, we're not eroding their spark plugs, it'll last longer, and since it can also ignite the fuel better, they can run the engines in an ultra lean mode where they can get more fuel economy. This market is expected to expand, but even then, we've actually also heard this earlier today, by 2035, we're still expecting to be having gasoline fuel dominating our transportation use. So the point of starting in natural gas is they have a time-critical need. They want to solve this problem now. They're willing to work with us in the R&D stage, get the technology to the point when they can put it in their vehicles, and they're willing to pay a premium. The automotive market does not pay a premium on ignition systems. It's a commodity. They need to be able to see a lower cost point. So what's our entry into automotive? Well, if you look at the CAFE standards, they need to improve their fuel economy by 26% by 2020. That's compared to 2016 now. And the way these automotive companies are doing this is by combining several different technologies, whether it's 1, 2, 3, 4, 5 technologies that give a few percent each. And what we've demonstrated at a national lab, so we've actually done this twice now at national labs, is that we can improve fuel economy by an average of 17%. And the way we do this is by enabling a combustion mode that the automakers already know about. It's called ultra-lean burn. If they're able to burn in this ultra-lean mode, the combustion temperature is lower, there are less NOx emissions, and the engine is more thermally efficient. They cannot currently do that with their existing spark ignition systems. So if you take a look at the market, it's about a $3 billion market for ignition. And what that comprises of is what's called a Tier 1 supplier. These are the suppliers like Bosch, Denso, Delphi, Visteon, Johnson Controls. They make ignition systems for the automotive companies. Rather than work with them directly and pigeonhole ourselves into an exclusive with one Tier 1 supplier, we've chosen to work with the OEMs. So that's taken some time to develop the relationships, to demonstrate the technologies, and that's where we are today. So again, we're funded entirely on revenue. We haven't taken any investment up to this point. We've put in our own money to get through the concept validation. It was extremely important that we had this validated by third parties. The National Lab, Sandia National Lab Combustion Research Facility that ran our technology first on a gasoline engine. It was a DOE-sponsored program and a GM-sponsored program. We recently repeated this study on a Ford engine, also a DOE-sponsored program at Argonne National Labs. I have both those papers on my booth. The Argonne paper comes out in a month. So this alpha prototype is an extremely important phase. Where we are right now is we actually have a device that's this big. This will be tested on a gasoline engine for the first time in January. I know you probably can't tell. I'm extremely excited about the size of this. It's very big in our field. We haven't seen any nanosecond pulse generators that can do what this can at this size. So we're really excited about demonstrating that. So if we're lucky enough to earn your vote, what we want to use the 100K for is to help accelerate this process, getting us to the January test. We need another engineer. We're 6 people. We're all working every day, including weekends. We have more work than we can possibly handle, which is good. It's exciting, and we all love it. But we need another pulse power engineer. We've already identified who those people are. We're also going to file some provisional patents. But look, this is more than about just the money. What actually got us into the auto industry finally was having this validated in peer-reviewed journals by expert scientists. That's what we're really looking for here, is you all are peer reviewing us right now. You can come and talk to me, you can ask me questions, you can look at the papers, learn about what we're doing. What we're really looking for is the support of the broader community. Hey, this is real. And you need that kind of validation with any kind of transformational technology. So this technology has more applications than just to energy. And I mentioned before, we like to focus on exactly what we're good at, which is nanosecond pulse power. We know that field. We're growing the team to be the best in the world at that field. So our first deployments are going to be in energy. It's going to be ignition, and it's going to be NOx remediation directly in the exhaust. But there are other deployments of nanosecond pulse power. We always like to say it's a hammer and everything looks like a nail. So there's health applications. So we're actually currently working on a cancer therapy. We decided we didn't want to be a medical device company, but USC has spun out the entity, licensed our intellectual property for the field of use of medical, and they're currently funding this effort. So we're actually seeing very good results in the FDA trials. So our vision for this technology is that in 10 years, every day of your life, all of you will interact with nanosecond pulse power, whether it's in the car you drive, the bus you take, the airplane you fly in, or the food that you eat that's been sterilized by our technology, or even a cancer treatment in the doctor's office. So with that, I just want to leave you with a very cool high-speed video of an optically accessible gasoline engine. On the right-hand side, you see our technology. On the left-hand side, you see spark ignition. This is actually combustion inside of the engine, comparing the two technologies. Thank you.
Thanks, Dan. Great stuff. Brad.
Two questions.
Sure.
One is, you're a technology company. Why are you positioning yourself to be a manufacturing company as opposed to letting that go off somewhere else and focusing on where your expertise is? And the other is, since this is ocean exchange, can you talk to us a little bit more about the exhaust treatment function and what it would take to get that in ships?
Absolutely. So thanks for your question. So for the first one, we are not positioning ourselves actually to manufacture the ignition system. We do currently manufacture the systems that we sell, the research systems, the nanosecond pulse power research boxes. But we're positioning ourselves to work with a strategic partner. The OEMs help facilitate the conversation. The tier one is going to manufacture this in the end. So the second part is the diesel emissions. I definitely want to talk more about this. But what we do is, essentially, we just stick a threaded rod down the pipe, and you just apply that high voltage very quickly and produce the plasma in the exhaust. This is not a new technology. We've known about this for 20 years. It just takes a while to get to this point. So what we've been focused on there is energy consumption. This technology really got ramped up in interest in early 2000. In fact, you'll see a lot of references to it in literature. And what happened was the energy consumption of the devices was too high. Yes, you can remove more than 90% NOx, even up to 98% in some of the papers, but the energy cost was more than 20% of the engine power, so it didn't make sense. So what we can do now is the trials that we did this weekend, we're at 4% of the engine power. We're targeting 1%. An SCR system, for example, in a marine diesel ship, I've seen a few numbers, but somewhere around 5-6% of the engine power for the current SCR system. Ours doesn't have to replace that system. We could excuse me, we could use it in parallel, but we could potentially also look at shrinking the size or eliminating that system entirely. Mm-hmm.
Next.
Thank you for the presentation. A question about the timing and the mixture, because obviously the way in which the fuel is distributed in the cell and the timing of when the pulse occurs, and the other part of that also is a question, is it a single pulse, or are you generating over any, multiple pulses? Because that'll affect how the distribution of that combustion occurs.
Yes, absolutely. That's a great question. So we do single pulse sometimes. In some cases where the engine load is very high, we do multiple pulses. The timing is very similar to what you're already doing with your spark, but we actually deliver the pulse a little bit later because it ignites quicker. So you have to adjust the timing. You do that through a reprogramming of an ECU. It's a relatively easy thing to do. So we do multiple pulses sometimes at repetition rates in the kilohertz range. And one of the things you kind of touched on is the timescales are very, very different. Over the course of a nanosecond, fuel is barely even moving, right? So you do have to, having that multiple pulse discharge really helps kind of put it in the right spot. Mm-hmm.
We have a question over here on the left.
Hi.
Hi.
So this is a minor point of clarification, but if you're operating in what is currently a dual fuel vehicle, does that go to, with your help, does that go to a single fuel vehicle instead? And if it does that change what goes on if there's a fire that has to do with this vehicle? If the vehicle catches fire on the road, is it going to burn at a lower temperature? Is it going to be easier to put out? That sort of thing, because you've taken the most volatile fuel out of the picture, or have I got that wrong?
It's a very good question. So the first part of it is we wouldn't use this in the dual fuel environment. So the point of doing dual fuel is to remove the ignition system and have compression ignition. And what we're trying to demonstrate is that we could get spark ignition and at similar compression ratios and still be able to ignite just natural gas. So that's what it'd be for that application. The other part's a very good question. So part of designing this alpha prototype that we talked about is the safety regulations. So we're looking at the auto regulations. Thankfully, because of hybrids, there's been a lot of pioneering work on pushing regulations on high voltages, because hybrids have high voltage in them. So our system is going to be very similar in terms of voltage to an existing ignition system. We're not pre-treating the fuel. It's not going to burn at a lower temperature. It's only in situ, in the cylinder, where that happens.
Okay, thanks.
Yep.
One over here.
From looking into your video where you had the appeared to be a faster compression and explosion taking place, overpressurization of the cylinder, is that a concern with engine wear?
So it's a very good question. So we're not actually leaving the fuel air mixture the same to get that rise in peak pressure. So what we're doing is we're leaning out the mixture. So you're putting in less fuel, but you're getting the same peak pressure, you're just using less fuel. So the performance of the engine feels the same, it's just less fuel per charge. So that's where you get the 20% fuel economy from.
Okay, thank you.
All right, Dan. Thank you very, very much.
Thank you.